Hello, everyone. Thanks for joining. My name is Imran, and I'm grateful to share with you our recent work on breaking Google's reCAPTCHA service using an object detection based solver. This is a joint work between the University of Louisiana at Lafayette and Xi'an Jiaotong University. To jump right in, I want to give a little background on reCAPTCHA v2. So, reCAPTCHA v2 is one of the most popular image capture services on the internet. It was first released by Google in 2014, but Google frequently updates the system to keep it secure against emerging threats. This figure shows the reCAPTCHA's "I'm not a robot" checkbox. Whenever someone clicks on the checkbox, the advanced risk analysis engine try to determine whether the user is a human or not. If the system is pretty certain the user is a human, then they will not be required to actually solve a challenge. Otherwise, the user has to solve the image capture challenge to pass the test. The current version of reCAPTCHA v2 shows two types of image capture challenges. The first one is selection-based capture challenge, where users have to select images from a set of candidate images to pass the test. For example, here the challenge instruction says select all the images with crosswalks. So user need to select all the images that contain crosswalk and then click verify to submit the challenge. The second one is click-based image capture. This is pretty similar to selection-based image capture challenge, but the only difference is when someone clicks on an image, it disappears and a new image appears in its place. The user has to continue clicking on the new images until no image containing the target object is left in the challenge widget, like this image, and then finally click verify. reCAPTCHA has been attacked before. Sibakorn et al. Cracked the initial version of reCAPTCHA v2 in 2016 using off-the-shelf image annotation services. They achieved an attack accuracy of over 71% in their work. Similarly, Wang et al. Used a convolutional neural network-based image classifier to break reCAPTCHA 2018 with an attack accuracy of 79%. So what's new in the latest version of reCAPTCHA v2? First, the reCAPTCHA v2 image challenges now contains complex everyday scene with common objects in their natural context. Second, it includes more object categories that were not available in the earlier versions. Third, the advanced risk analysis engine, the advanced risk analysis engine is more improved right now. Fourth, the reCAPTCHA can now use different kind of anti-recognition mechanisms such as noise, distortion, etc. to disable machine learning-based recognition technologies. So in our work, we make the following contributions. First, we show that off-the-shelf vision APIs for image recognition and deep neural network-based image classifier are no longer effective against the latest reCAPTCHA v2 image challenges. Second, we propose a highly efficient and effective object detection-based solver for breaking reCAPTCHA v2 image challenges. Third, we provide a comprehensive security analysis of different security features employed by the latest version of reCAPTCHA v2. So first, we tried to break reCAPTCHA v2 image challenges using vision APIs for image recognition. We use 4 different image recognition services. The first one is Google's Cloud Vision API. Then we used Amazon Recognition, Microsoft Cognitive Services, and Clarify. This table shows the attack success rates of different image recognition services. The Google Cloud Vision API achieved the lowest success rate, which is 19%. On the other hand, Amazon Recognition achieved an accuracy of 47%. Then we try to break reCAPTCHA challenges using a deep neural network-based image classifier. We actually use a convolutional neural network image classifier, which are good at recognizing, which are actually good for image classification tasks. So we perform a live attack using CNN-based image classifier, and we got only 21% accuracy while trying to crack the challenges. So we can see that Bayesian APIs for image recognition and deep neural network-based image classification models provide really poor performance against the recent reCAPTCHA V2 image challenges. So this motivated us to use an object detection-based solver to break the reCAPTCHA's most complicated image challenges. This figure shows the overview of our CAPTCHA backend system. It has 2 modules. The first one is a browser automation module, and the second one is a solver module. The browser automation module is responsible for automating browsing-related activities. For example, it is responsible for initiating the challenge, extracting the target object's name from the challenge instruction, identifying the challenge type, whether it is a selection-based CAPTCHA or click-based CAPTCHA, fetching the challenge images, submitting the challenge, and verifying the solution of the challenge upon the submission. The solver module is responsible for detecting and localizing target objects and mapping the target object's location to the potential grid number in the original reCAPTCHA challenge widget. Here we provide a brief detail of our solver module. The core component of our system, solver module, is a object detection system. So the object detection system takes a challenge image and detects all the objects in the images and keep their objects' names and locations in terms of bounding boxes. So once we know the target object's location, we need to map the target object's locations or bounding box coordinates to the potential grid number in the reCAPTCHA challenge widget. This figure shows a original reCAPTCHA image challenge. Here we can see we can represent the image as a set of grids. Here, this number shows the grid number like 0, 1, 2, 3, 4, 5, 6, 7, and 8. So here the target object is a bus. Once our object detector identifies all the buses in the image, it gives us the bounding box, and then bounding box to grid mapping algorithm gives us the potential grid number for the bounding boxes. Here we can see our potential grid numbers are 0, 2, and 3. Attack evaluation. So for implementation and evaluation platform, so for building the browser automation module, we use Puppeteer Firefox library, which is developed by Google for controlling the Firefox web browser automatically or programmatically. And we also use custom JavaScript code for developing our browser automation module. And our solver module, for our solver module, we used YellowB3 object detector as a object detection system. And we use two datasets to train our models. The first one is a MS Coco dataset, and the second one is a custom dataset. We tested our system on a server with 6 Intel Xeon CPUs and NVIDIA GeForce RTX 2070 GPU. The system has 96 gigabits of RAMs, and it is running the Arch Linux operating system. The overall accuracy and speed. So we submitted 788 live challenges to 4 reCAPTCHA protected websites. The attack accuracy is 83.25%, and the average speed of our attack is less than 20 seconds. This table shows the time required to break a reCAPTCHA challenge by percentiles. Attack performance on selection-based image capture challenges. So we evaluated the performance of our attack separately on both selection-based image capture and click-based image capture challenges. For selection-based image capture challenge, we can see we achieved an accuracy of 84.74%, and our system takes less than 80 seconds to break a selection-based capture challenge. We encountered total 19 object categories in the selection-based capture challenges. And from this figure, you can see if we consider only the top 5 object categories, it constitutes over 78% of the total challenge images. For click-based capture challenges, we identified only 5 object categories, and our system achieved an accuracy of attack of 71.26%, and the average speed of our attack is 43.53 seconds for a click-based capture challenge. Here we'll describe some of our other findings on reCAPTCHA. First, to see if the browser automation software has any impact on the attacker accuracy or performance, we developed a bot using Selenium, which is one of the most popular web automation software out there. We use both Firefox and Chrome web drivers for Selenium, and we achieved an attack accuracy which is below 40% for both Firefox and Chrome web drivers. And we noticed reCAPTCHA frequently blocks Selenium-based bots. But at the same time, when we use Puppeteer Firefox-based framework with exact almost same settings, we find that we can bypass this restriction. Impact of security preference. reCAPTCHA video supports 3 levels in the security preference settings. When a website owner wants to deploy reCAPTCHA on their website, they can adjust the security level in the security preference settings. It supports 3 levels of security preferences, which are easiest for user, moderate secure, and the most secure. We submitted 100 challenges for these settings, and we obtained almost similar performance. But as of July 2020, we noticed that reCAPTCHA actively blocks both Puppeteer and Selenium-based framework when the website uses most secure security setting. Impact of anti-recognition. We try to study the impact of anti-recognition on attackers' performance, or what kind of anti-recognition techniques reCAPTCHA uses to disable recognition by deep learning-based applications. We identified 52 images from all of the images which include some kind of noises and distortions. This figure shows a noisy image from reCAPTCHA challenge and label sets returned by 4 image recognition services. The target object here is a fire hydrant, and the potential grids number are grid number 1, 3, and 4. We can see that Google Cloud Vision API misclassified all of the grids. For example, it recognized grid number 1 as leaf, grass, plant, grid number 2 as art and pattern. For Microsoft Azure Computer Vision, it misclassified the first image, which is an image of a fire hydrant, the first grid, which contains the target object fire hydrant, but it identified it as animal and mammal. Similarly, Amazon Recognition and Clarify API also misclassified some of the grids. So this figure shows the result of noisy grid classification by image recognition services for all 52 images. Here, the column EM means number of exact match level sets. A means number of acceptable level sets. A means number of empty level sets, and MC means number of misclassification level sets. We can see that all of those image recognition services misclassified a significant number of potential target grids. For example, Google's Cloud Vision API misclassified 41 out of 172 potential grids. So from this result, we hypothesize that reCAPTCHA is likely to be injecting adversarial perturbation in some of those distorted and noisy images. Next, we try to study the impact of interrecognition on object detection models. So here we can see that our base object detection model could identify 114 out of the 203 potential target objects in the 52 images. But when we retrain our object detection model using basic augmentation techniques such as Gaussian noise injection and blurring, etc., our detection accuracy improved by 17%. Similarly, when we use adversarial training, the performance further improved, and it is improved by 26% compared to the base detection model's performance. We also studied the IP rate limit nature of the reCAPTCHA v2. We attempted to initiate 1,000 challenges each day to a reCAPTCHA enable website from 3 different IP addresses: an academic IP, a residential IP, and a Tor network IP. For academic and residential IP, we were able to initiate more than 800 challenges each day out of 1,000 challenges. So it shows reCAPTCHA follows a relaxed IP rate limit toward regular IP addresses. However, when we used Tor network IP, we found that reCAPTCHA blocked about 30% of our initiation attempts. So it shows that reCAPTCHA consider request coming from Tor exist node highly suspicious. We also did a performance analysis to try to see how our system fare against human-based CAPTCHA solving services. We used 5 CAPTCHA solving services, which are 2-CAPTCHA, anti-CAPTCHA, based CAPTCHA solver, dead by CAPTCHA, and image typers. For all of these services, the 2-CAPTCHA achieved the highest accuracy, and the best CAPTCHA solver achieved the lowest accuracy, which is 67.2%. They are pretty accurate. However, if we look at the speed, you can see that the fastest CAPTCHA solving service, which is 2-CAPTCHA, takes 73.11 seconds, where our system takes less than 20 seconds to solve the CAPTCHA, which shows that our system is highly efficient and could be used to perform a large scale attack on reCAPTCHA v2 image system, image CAPTCHA system. So we recommend the following countermeasures to prevent our attack or slow down our attack. First, we recommend that reCAPTCHA should incorporate natural language understanding to image capture test. Natural language understanding is one of the biggest challenges in natural language processing domain. So this weakness could be exploited to make the capture system more difficult for the bots, at the same time making it easy for the humans, because human could naturally understand such language. Okay, similarly, the use of special properties of the object, such as shape, orientation, etc., could be used to make the challenge difficult for bots, or make the bots make it difficult for the bots to identify the target objects correctly in the challenge images. And content heterogeneity as well could be used as a potential countermeasures. So in the conclusion, we can see that reCAPTCHA B2 can defend against image classifier-based solver to a greatest extent. We could see that image classification-based technologies provide a really poor performance against recent reCAPTCHA B2 image challenges. And we can see that the advances in object detection technologies pose a serious threat to the image capture systems. Although our system is specifically developed to crack reCAPTCHA B2 image challenges, we think similar attack could be applicable against other image capture systems that rely on object recognition as the underlying AI problem. And third, the updated security features employed by reCAPTCHA are not sufficient to prevent automated abuses. Here are the references. Thanks for listening. I'm happy to take your questions.